Geometric isomers are referred to as cis-trans isomers. This is only a possibility, and it's not all the time, but the only time you can consider geometric a possibility, which we're going to get into next week, the only way you can even consider geometric a possibility is on what's referred to as alkenes. And cycloalkanes. So an alkene means that you have at least one carbon-carbon double bond. Again, I'm going to get into that next week. A cycloalkane means that it's a cyclic structure with all single bonds. I'm going to go over what, again, I don't think we have time to get to that tonight, so I'm going to go over that next week. Once I introduce what an alkene and a cycloalkane are, I'll come back to that part. So as far as different, what do you think the key is that something's different? If the number of atoms are different, there's nothing else to look at. If the number of atoms are different, they can't be the same if they have a different number of atoms, and it can't be isomers if they have a different number of atoms. The definition of an isomer is the same number of atoms for a different arrangement. So when you've got a problem like this, if I give you a couple of pairs of structures and I ask you, are these identical, are they different, are they constitutional, are they geometric? First thing that you should be ruling out is whether or not they're different. The first thing you want to do is you count the number of atoms. If the number of atoms are different, there's nothing else to look at. It can't possibly be anything other than they're just different structures. So the first step is to count out the total number of atoms. Now, say I had this structure. This is called butane. You don't need to know that yet. We'll go over that next week. Say you got that structure. In order to know the number of atoms, you got to get the molecular formula. So, how many atoms do you have in that structure? What is the molecular formula of that structure? How many carbons do you got?
4.
You got 4. How many hydrogens do you got? 10. If you wanted to count that out, this carbon has 1 bond, it needs 3 more, so it's got 3 H's. This carbon has 2 bonds, it needs 2 more, so it's got 2 H's. This carbon has 2 bonds, it needs 2 more, so it's got 2 H's. This carbon has 1 bond, it needs 3 more, so it's got 3 H's. Count it up, you got 3, 2, 2, 3, you get a total of 10 H's. Structure like that's not so bad. You got a structure like this. Probably not going to sit there and have to count the number of hydrogens. So there's a quicker way of identifying how many hydrogens you have. Again, this is why the placement of this topic really should not be in chapter 1, because you don't really get the quick shortcut in counting these until chapter 3, so I'm going to mention that now. If you want to identify how many H's you have, there's a formula that you can use in order to calculate that. When you go to figure out how many hydrogens are within the structure, the number of H's is going to be based off the number of carbons within that structure. So you're going to follow what's referred to as the saturation formula. Saturation means that you have the maximum number of hydrogens possible. So when you talk about saturated fat versus unsaturated fats, this is what they're referring to, is how many H's do you have in your structure. If you have the maximum number of hydrogens possible, it's saturated. If you have a reduced number for the maximum number possible, it's referred to as unsaturated. The saturation formula, the maximum number of hydrogens that an organic compound can contain, is determined by CnH2n plus 2. Meaning that the number of H's is going to be based off of how many carbons that you actually have in the structure. The number of carbons is your N value, and you're going to need that N value to figure out how many H's you should have in your structure. So if I wanted to look at this structure real quick, again, this one was easy enough to actually draw the hydrogens in, count them out, and figure it out. But if you didn't want to sit there and count those 10 H's, you just wanted to quickly get it. There's 4 carbons here. So there's 4 carbons. You go to that CnH2n plus 2 formula. If there's 4 carbons, then your N value is 4. So you're going to plug the 4 in to the rest of the equation. If you do a quick calculation, 2 times 4 is 8, plus 2 is 10, and that's what gives you your molecular formula. If it's a small structure, it's not a big deal to sit there and do the number of H's. And quite frankly, the problems that I give you on the exam won't be that, they won't be the smallest things, but they'll be small enough that if you needed to sit there and actually plug the H's in, you'll be able to do that. I would recommend trying to get used to not having to do that in your formula, particularly for anyone here that's studying for any of the pre-professional exams. A big key on those tests is time saving rules, so I would try to use shortcuts as opposed to actually sit there and open an entire structure up in order to do it. But if I wanted to quickly figure out how many hydrogens were within the structure, all you have to do is count the number of carbons. And I count the number of carbons, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, a total of 15 carbons. If you can do that, you can then quickly figure out how many H's you got. You take this formula, you've got 15 carbons. That number of carbons is your N value, so I'm going to take that and plug that into the rest of the equation. And if you do quick math, 2 times 15 is 30, plus 2 is 32. So the formula here is C15 H32. And now you know exactly how many atoms you have without actually having to sit there and count every little thing. This is more important when you get to the larger, more complex structures. Again, the ones on the test, it'll definitely be a time saver if you don't have to sit there and count it, but they'll be manageable enough that if you need to sit there and count it, you'll be able to sit there and count it. What you can do then is this can be adjusted for other types of structures. Say I was dealing with stuff that had double bonds, say I was dealing with stuff that had rings. Those make slight alterations to it. What you do is this formula is your saturation formula. Things that are unsaturated will have less H's than this formula. Saturation means max that you can have. When this refers to saturation, it's referring to the number of hydrogens. So if you can figure out how many H's are the maximum total you could possibly have, and that's your saturation point, any of these other things you add to the structure, all it's going to do is knock that number down. If you don't have the maximum number of H's, you're referred to as unsaturated. You'll know you're unsaturated because you'll have double bonds, you'll have multiple bonds. Or you'll have rings. So you'll have multiple bond and or rings within the structure. Basically what you're going to do is every multiple bond you got, or every ring that you've got, you're going to take 2 hydrogens away from what that saturation value should be. I'll show you how that works. On a problem like this, first thing you want to do is identify, are they different or are they something else? The only way they're different is with a different number of atoms. The only way they're identical or constitutional is if it's the same number of atoms. So your first step is to figure out how many atoms you got. So if I had a structure that looked like this, and I had a structure that looked like this, I ask you, are those identical? Are they different? Are they constitutional isomers? Are they geometric isomers? Right now, geometric is not the wrong answer, but I haven't told you that yet. So you're going to be taken from identical, different, constitutional. Identical means same atoms, same bonding pattern. Constitutional means same atoms, different bonding pattern. Different structures just have different number of atoms. So your first step is, as different as they might look, they might not be different. They might not be classified as different structures. The only way to look, they're just solidly different if the number of atoms is different. So quick take a look at this one. How many carbons you got here?
6.
You got 6. How many carbons you got here?
5.
You got 5. You don't got to do anything else. Do you have the same number of atoms? No. You got to look at the hydrogens. The hydrogens are irrelevant because they have a different number of carbons. If the number of atoms are different, if they're just different. There's no other possible answer. As soon as it's a different number of atoms, the answer says they're different. But say you had something like this. Say those two structures. Okay, same thing. Are they identical, are they different, or are they constitutional isomers? First step you got to do is you got to count up what the total number of atoms are. So you look at the structure on the left. How many carbons you got in the structure on the left? 6. How many carbons you got in the structure on the right?
6.
6. So far you don't have a difference yet. And you still got to look at the hydrogens. You need to look at the heart. All the atoms have to match in order for them not to be different. So the number of carbons hasn't given me any difference yet. So now I'm going to look at the number of hydrogens. So I'm going to come to the one on the right. If I look at the one on the right, for anything, if you want to figure out the number of hydrogens, you use this formula. And then for every ring or for every multiple bond, you knock the number down by 2. But you always start out, always start out with the full-fledged saturation formula. Starting with the saturation formula. With the saturation formula, how many H's? If you have 6 carbons, what is the maximum number of H's you have? What is the saturation number of H's you have? That would be 14, because if your N value is 6, 2 times 6 is 12, plus 2 is 14. So, looking at this structure, maximum number of H's that I could potentially have is 14. Okay, that's the saturation number. Number 6 carbons, the maximum number of H's you can have is 14. It's a CnH12 plus 2. What you're then going to do is you're going to adjust these if necessary. The only time you got to adjust it, if there's a multiple bond, for every multiple bond, you knock 2 H's off. If there's a ring, for every ring, you knock 2 H's off. So looking at this structure, do you have any rings? No. Do you have any multiple bonds? No. At that point, you can't make any adjustments. This holds. This is the formula for this structure. If I look at this structure, does it have any multiple bonds? No. Does it have any rings? The answer is yes. It has 1 ring. For every ring you got, 2 H's get knocked off of it. Which means that the formula for this is actually C6H12. If you wanted to, you could have gone through and counted that out. You could have said that this carbon has 1 bond and needs 3 more. This carbon has 3 bonds and needs 1 more, 2 bonds, 2 more, 2 bonds, 2 more, 2 bonds, 2 more, 2 bonds, 2 more. Counting them up, and you would have gotten your 12 H's as well. And you could absolutely sit there and count the H's if you wanted to. Now looking at this is a C6H12, that's a C6H14. Different number of atoms, they're different. There's nothing else to look at. Once you know what the atoms are, if they're a different number of atoms, they're just automatically different. Now say you got these 2. Again, 2 structures that look extremely different from each other. So looking at the structure on the left, how many carbons do you got? You got 6. Looking at the structure on the right, how many carbons do you got? You got 6. What's the maximum number of H's you could have if you have 6 carbons? So like this formula. Again, if you have 6 carbons, 2 times 6 is 12, plus 2 is 14. If I have 6 carbons, maximum number of H's I could potentially have is 14. never going to do any adjustments that I need to. For every ring you got, you knock it down by 2. For every multiple bond you got, you knock it down by 2. So in this case, I got 1 ring. If I got 1 ring, I'm going to knock that down by 2. And alternatively, you could sit there and count up all the carbons and H's, and if you did that correctly, you come out with C6H12. If you look at the one on the right, you may not have a ring, but you do have 1 multiple bond. For every ring, for every multiple bond, you knock this number of H's down by 2. And again, you don't have to do this. You could have sat there and counted the number of carbons, the number of hydrogens, it would take you longer. But doing that, looking at these have the exact same number of atoms. At this point, different is no longer an option. If it's identical, there's different, it's constitutional. The only way they can be different is if the number of atoms are different. But the number of atoms are not different, the number of atoms are identical. So out of the 3 choices, the difference out, you're either dealing with an identical set of structures or you're dealing with constitutional isomers. This is a situation where it's pretty clear cut. These are definitely not the same structure. There's no way at all that these are the same structure. One's a ring, one's not a ring. There's just any number of things you look at say they're not the same structure. So if they're the same number of atoms, they're either identical, which sometimes is hidden, there's no hiding that, they're definitely not identical, or they're constitutional isomers. Constitutional isomers means the same number of atoms, different arrangement. Sometimes it's a subtle difference in the arrangement, sometimes it is a massive difference in the arrangement, but the definition of a constitutional isomer is same number of atoms, different arrangement, same number of atoms, clearly a different arrangement. These are going to be classified as constitutional isomers. So you have that set of structures. And you have 2 structures in front of you. Are they the same? Are they different? Are they identical? First thing you want to do is identify what the number of atoms are. Different number of atoms are different. Same number of atoms are either identical or they're constitutional. So taking a look at this, the one on the left has a total of 6 carbons. The structure on the right is a total of 6 carbons. If I want to know how many H's there are, I'm going to start with my saturation formula. So if I have 6 carbons, again, 2 times 6 is 12, plus 2 is 14. You couldn't go through and just count the number of H's. So this is C6H14. This is C6H14. And you're going to take a quick look and see if you've got to adjust it. The only way you adjust it, if you have a ring, you knock it down by 2. If you have a multiple bond, you knock it down by 2. Neither one of them has any rings. Neither one of them has any multiple bonds. Neither one of them gets adjusted. So they're not different. The answer is definitely not different. They're the same number of atoms. So now the question is, are they identical or are they constitutional? Just because they look different does not mean that they're automatically constitutional. We're looking at our bonding patterns, like they did over here. What you want to look at, what is the longest continuous carbon chain you can touch? And anything that's not in that longest chain, where is it hanging out relative to the rest of the structure? So if I look at this chain right here, if I look at this structure, what's the longest continuous chain of carbon you can touch without looking at a ton of paper? 5. 1, 2, 3, 4, 5. This carbon that I have not accounted for, where is that positioned along the structure? Number-wise, 3. It's smack in the middle. I can count from the left, I can count from the right. Either way, it comes out 3 positions. So I can touch 5 carbons continuously, and that 1 carbon I can't touch is on the 3 position. If I look at that structure, which does look different, what is the longest continuous chain of carbons you can touch without looking at pen on the paper? In this case, it's 5. You can touch, if you want to get to the center, it's 1, 2, 3, 4, but I can do 1, 2, 3, 4, and 5. So I can touch 5 continuous carbons. I have 1 remaining hanging out, and relative to the rest of the chain, what position is that extra carbon hanging out at? It's at the 3 position. In both of them, I have the same number of atoms. In both of them, they have the same longest continuous chain. In both of them have a single carbon hanging out on the 3 position. Everything about these is the same. Same number of atoms, same bonding arrangement. These, in this case, are going to be identical structures. As far as isomers, I generally don't ask you to go and draw a whole bunch of isomers. It's more I want you to be able to look at a couple structures and do a comparative look at them, identify are they identical, are they different, are they identical. The only other possibility again would be geometric. I'll mention that next week briefly. The geometrics are pretty easy to pick out when you have them. It's pretty obvious when you're dealing with geometric when you're not dealing with geometric. The 3 ones that tend to get students tricked up are identical or different and constitutional. So again, count number of atoms first. Number of atoms are different, they're different. Number of atoms are the same, they're not different. If the number of atoms are the same, they're either constitutional or they're identical. The only way to know that is to kind of pick it apart and look at what the bonding arrangements happen to be. Sometimes it's obvious that they're the same number of atoms and they're definitely not the same arrangement. Sometimes it's not so obvious. So the structures that don't have one's arranged, one's not, you have to look a little bit closer, identify the longest chain, identify the stuff that's hanging off, and identify where it's hanging off. This type of mentality is exactly the type of mentality you use when you're naming a structure. So this will make a lot more sense and get a lot clearer when we do the nomenclature next week. Because the rules I'm using to help you classify the bonding patterns are exactly the same rules you use when you go to the naming. So once we go through the naming, then this whole method is going to be a lot. You're going to see how it fits into it a lot better. But as far as isomers, again, that's pretty much it. I'm going to go over geometric next week, but I'm going to do a little bit on chapter 2 just to get some of this out of the way. I'm going to be sending out practice problems a little bit closer to the test, so you'll get a feel for what I'm asking. You'll see they're very similar to what I'm doing on the board. I already know what's pretty much what's going to go into it, so the practice problem is going to be very similar to it. But any questions on the isomer? Yeah.
So the carbon chain can be any way possible in terms of like
any direction, up, down, left, right, diagonal. Only thing you can't do is you can't look at the pen and you can't backtrack. So once you're not doing that, start anywhere and anywhere.
Is that should be up and out before
So when we go through the name, this is the naming process. You got to find, it may not be this chain right down the middle. You find a long continuous chain and name it. So when we go through the naming, it's going to help you enforce the methodology. All right, as far as chapter 2, chapter 2 is a couple of scattered topics. It's not a whole lot to it. And you don't necessarily need everything that's in that chapter, so I'm going to kind of do what I feel are the important parts, not doing everything from chapter 2 though. So if you are looking through the textbook, just to make sure that you're not going through some unnecessary sections that we're not covering. Again, I'm kind of choosing what I want to go over as far as chapter 2 goes. Most of the stuff that's in here is relatively simple. Some of it's going to require a little bit of memorization. The chapter ends with what are referred to as functional groups. If I don't get to functional groups tonight, I sent you a handout in your email, which there's a lot more functional groups in the book than what I want you to know. The stuff that I sent in the handout, those are the ones that I want you to know for the exam. Functional groups are reactive points on the structure. They're where the stuff's going to happen. Generally, when you know the stuff's going to happen, there's oxygens, there's nitrogens, there's polar bonds on the structure. So as far as the functional groups, if I don't get to it and you want to get a head start on it, what I would suggest doing is take a look at the handout, see which ones I want you to know. The way those are going to show up in a problem, I'm going to give you a relatively big structure. Usually I pick some type of pharmaceutical compound. And you're just going to go through. I'll probably circle a couple of functional groups and ask you, what are they? So know what an ester looks like, know what an ether looks like, know what a ketone looks like, know what an aldehyde looks like. It's relatively easy points on the exam. It's usually about a 5 or 6 point question on the test. And it's literally just recognize functional groups. No further understanding or in-depth comprehension of it. It's just recognizing them. So if I don't get to it tonight, next week, before next week, print out that handout, look it over. I want you to be able to take the functional groups on that sheet and identify them within the structure. Be able to identify an ester in the structure or an aldehyde in the structure, and so on. Now when I get week. I'll mention a couple particulars about each one, but you should have seen it at that point. All right, so for chapter 2, it's largely dealing with acid and bases. I'm not getting it. There's only certain parts of the acid base theory that you have to know. There's not a lot. Most of the stuff you dealt with in general chemistry, you're not going to see in this course. You're definitely not doing buffers or titrations. You're not doing Ka or pKa calculations. You have to be able to recognize what a pKa value or Ka value is telling you about the strength of something, but you're not doing any calculations as far as this course. There's 2 small calculations you will do, and none are in this chapter. So as far as the acid base, it's way more theoretical stuff than quantitative type of calculations. But as far as some of the smaller stuff in this chapter, you have what are referred to as dipole moments. Those are caused by the polar bonds. I kind of went through that last week. If you have 2 atoms that are different, one's electronegative, one's really not electronegative, the electrons will exist a little bit closer to the more electronegative one, creating poles. So when you look at different structures, certain structures are going to be labeled, are going to have dipole moments, and they're going to be labeled as non-polar molecules or polar molecules. What I want you to be able to do is basically looking at a structure, I want you to be able to identify what the intermolecular forces are that are exhibited by that structure. I'm not going to ask you to do anything when you're drawing these arrows. And I think there may have been a couple problems in the homework where they asked you to draw the arrows. That's just more to get you used to how the electrons move. I'm not going to ask you to draw any of these types of arrows in the actual exam. What I will ask you is, given a couple of structures, be able to identify what types of intermolecular forces are exhibited. So as far as intermolecular forces in general chemistry, I know that some professors go over it, I know some professors don't. I'm not going to get incredibly in-depth on it. It's more just recognizing it. The reason why I want you to be able to do this is because it makes a relatively easy problem on the exam, and it helps to move down some of the more difficult stuff. So I'm trying to get a lot smaller, easier type questions in. As far as intermolecular forces, there's 5 of them. In terms of strength, the top are referred to as ion-ion. Then it goes ion-dipole. Then it goes hydrogen bonding. Under that is dipole-dipole. Hydrogen bonding technically is dipole-dipole, just an ultra strong one. And then under that is London dispersion. I mentioned last week that we're not dealing with ionic structures, which are nice, because then that means that this will never be a possibility, and this will never be a possibility. So for all intents and purposes, for this course, you only have to deal with 3 intermolecular forces. The 3 that you should be dealing with are hydrogen bonding, dipole-dipole, and London dispersion. As far as identifying molecular forces, if something has hydrogen bonding, there's 2, this is where the problem can be tricky. I generally will ask you for what is the strongest intermolecular force exhibited. Molecules can exhibit more than one type. I'll generally ask you what is the strongest type that's exhibiting. I have seen on pre-professional exams where it asks you for all the intermolecular force exhibited. So if they reference intermolecular forces, make sure you're answering the question they're asking you. There's a difference in what is the strongest type it's exhibiting versus what are all the types that it's exhibiting. General rule of thumb is wherever you're at, it includes that plus everything under it. So something that is hydrogen bonding also exhibits dipole-dipole, and it also exhibits London dispersion. Something that exhibits dipole-dipole will also exhibit London dispersion. Something that exhibits London dispersion will only exhibit London dispersion. So if you're up here, you're looking for everything. If you were up here, if you're structured hydrogen bonding, if I ask you what is the strongest that it exhibits, it's hydrogen bonding. If you were asked what are all the forces it exhibits, it's hydrogen bonding, dipole-dipole, and London dispersion. And I'm going to ask you what is the strongest type that it exhibits. But I have seen pre-professional exams that ask what are all the types that it exhibits. So be careful of what it's asking you. Because if your structure is hydrogen bonding, and they ask you for all of them, they'll actually have a choice where it's just hydrogen bonding. Another choice where it's all three of them listed. And again, if you have dipole, it includes that, puts everything under it, so it means you also have lung dispersion. If lung dispersion is the highest, well, there's nothing under that, so that's all that you got. The way you're going to identify what you have, if your structure is nonpolar, the highest that you can exhibit is lung dispersion. How can you tell if it's nonpolar? Relatively the same electroactivities, which carbon bonds who have zero polarity, they're the same. If you have a bond between the same types of atoms, then it's clearly nonpolar because the electronegativity is zero. What was the other type of bond I mentioned last week that's nonpolar? That normally was not C's and H's. So if your structure only has C's and only has H's, it's nonpolar. What would you have to have in the structure in order to exhibit polarity? Oxygen or nitrogen or a halogen or one of the other atoms that we're focusing on. If you have just carbons and you have just hydrogens, it's nonpolar. If you throw oxygens in, you're polar. If you throw nitrogens in, you're polar. If you throw sulfurs or phosphorus or halogens in, you're polar. So the only way that something is going to exhibit just lung dispersion is if it has nothing but carbon and hydrogen in the structures. If you have oxygen or if you have nitrogen or if you have something else, then that means that you're going to be on one of the higher tiers because then you're polar. These top two are specifically going to work with polar structures. So if it's non-polar, meaning nothing but carbon and hydrogen, the highest force it's going to exhibit is lung dispersion. If there's an oxygen or a nitrogen or something else in it, then it's going to be one of the top two. It's going to either be dipole-dipole or it's going to be hydrogen bonding. So the way you'll know which one of those it is, hydrogen bonding means that you're going to have OH or NH bonds within the structure. It's just dipole-dipole if it has no OHs or NHs within the structure. So if I were looking at each one of these and I want to identify what the strongest intermolecular force is that each one is exhibiting, well, first thing you want to identify is the polar versus non-polar thing. And if it's non-polar, there's only one choice. If it's polar, then you look a little bit closer at the structure. Again, the only way it's polar is if it has something other than carbon and nitrogen involved in the structure. So looking at these, as far as this first structure, this first one is nothing but carbons, nothing but hydrogens. It's non-polar, so the highest intermolecular force that it's going to exhibit is lung dispersion. If I look at the second one, this is if there's oxygens or nitrogens, and again, nothing's 100%, but generally speaking, if you have oxygen or if you have nitrogen or if you have halogens, you can generally assume that's going to be polar. So this is oxygen, you can assume that that's got some polarity to it. So if it's polar, that means it's going to be one of these two. So then you have to ask yourself, well, does it have OHs or NHs, or does it not have OHs or NHs? So this structure does have O's, and it does have H's. It doesn't have them connected to themselves. In order for hydrogen bonding, the oxygen has to be directly connected to a hydrogen, or the nitrogen has to be directly connected to a hydrogen. Simply having those pieces doesn't make hydrogen bonding. So this is polar, but it's got oxygen. It does have oxygens. It does have hydrogens. If they're not connected, then this rule does not apply. So if it's polar, the only way it's going to have hydrogen bonding is if it actually has oxygens directly to H's or nitrogens directly to H's. If it's polar and you don't have that, then it's going to be dipole-dipole. So this is dipole. This is going to be dipole-dipole. It's polar, but it does not have OHs and it does not have NHs. And for the third one is polar, but it has oxygen. And then taking a close look at it, it has an oxygen directly connected to a hydrogen. So the highest intermolecular force this will exhibit is going to be hydrogen bonding. chapter 2. Sorry, quick chapter. Any question on that? I know the question very similar to that. Mention this quickly. As far as the boiling point of alkanes, you're going to find that I really don't do anything with physical properties. I normally don't ask you questions about comparing boiling points or comparing melting points. The only one that I do that on is for alkanes. And that's because if there's any structure or any group that a pre-professional exam is going to ask you that about, it's most likely going to be with alkanes. It's kind of a classic example when they ask about boiling points, melting points. Outside of this chapter, I'm never going to compare boiling point. I really don't get into physical properties as far as this course, except for this one topic. So if you are looking at alkanes and you wanted to just generally say what is a higher boiling point, what has a lower boiling point, there's two things you're looking at. You're looking at the number of carbons, and you're looking at the number of branch points. So number of carbons is easy. You count the number of carbons. Without question, more carbons, higher boiling point. Without question. If something is 6 carbons and something is 5 carbons, the one with 6 carbons absolutely 100% will have a higher boiling point than the one with 5 carbons. You don't look at any, it doesn't matter what the structures are, what one is branching, one isn't branching. If something has more carbons than something else, it automatically will have a higher boiling point. So anything with 6 carbons is going to have a higher boiling point than anything with 5 carbons is going to have a higher boiling point than 4 carbons, 3, and 2, and 1. If they have the same number of carbons, that's when you look at branching. So if I've got 2 structures, one is 6 carbons, one is 5, I don't got to look at anything other than number of carbons. More carbons, higher boiling point. If I've got a couple structures that have the same number of carbons, that's when we look at branching. So what branches are is kind of what I was doing with this stuff. You find your longest chain. Anything that's not part of that chain is considered a branch. It's a position or a branch point coming off that longest chain. So if I were to look at that first structure I can touch all 5 carbons without lifting the pen off the paper. It has nothing else hanging off of it. It would be said to have no branch points. Nothing is branching off of that longest chain. If I look at the structure in the middle, I can touch 4 of those carbons, leaving 1 hanging off. So that 1 that's hanging off is 1 branch point. If I look at the third structure, I can touch 3 of those carbons continuously, leaving 2 remaining carbons. Now we have 2 branch points. The more branch points you have, the lower the boiling point. So there are 2 rules. More carbons equals a higher boiling point. More branching equals a lower boiling point. And again, it's a hierarchy in terms of those rules. So you don't look at rule number 2 unless they have the same number of carbons. Anything with more carbons absolutely has a higher boiling point than anything with less carbons. It's only the number of carbons are the same. You got 5 carbons, 5 carbons, 5 carbons, that you would then look at the branching. More branching results in a lower boiling point. The reason why, when you boil something, you're turning it into a gas. You take these molecules and you spread them really far apart from each other. In order to turn into a gas, you've got to take 2 molecules that are relatively close in the liquid state and pull them apart. So the more surface area that comes in contact, the more force, the more strength you have to overcome in order to break those. The less contact these molecules have with each other, then the easier it's going to be to pull them apart. So when you have straight chains, if I've got a straight chain, when I got 2 of these next to each other, they are literally going to lie right on top of each other. All of that force in between it, all the intermolecular force in between it. Intermolecular force means the force between molecules holding them together. So when I have 2 straight chains, I have a whole bunch of intermolecular force holding these things together. In order to get this to boil or turn into a gas, I've got to break all of this force in order to get them to pull apart. The more force I'm going to break, the more heat that's got to go into it, the higher temperature it's going to require. If I got something that branches, lie two of these next to each other, you're only going to have a minimal amount of contact between them. You have less force that's got to be broken in order to pull these apart. Less force has got to be broken, lower temperatures, lower boiling points. So the more branching you have, the further these things are from each other, they're already kind of pulled apart at that point. It's going to take a lot less heat in order to finalize that in terms of the gaseous state. The less branching they have, the more they are in contact with themselves, and the more force you're going to have to overcome. So again, the two rules as far as, if I give you 3 or 4 or 5 alkenes, first thing you do is count the number of carbons. More carbons at higher boiling point than anything with less carbons. Anything that has the same number of carbons, you'll then evaluate how many branch points it's got. The more branch points you have, the lower the boiling point of that particular material. So if I gave you 3 compounds, say, if I gave you 3 structures, say you had structure A, and structure B, and structure C. And I asked you, what is the highest boiling point out of all 3 of those structures? Which one of those has the highest boiling point? C. Answer A. Why is the answer A? It's got the most number of carbons. First thing you look at is the number of carbons. Doesn't matter what the relative structures are. More carbons automatically, it's more atoms. More, which inherently is going to have more surface area and more bonds to break. More carbons, higher boiling point, automatically. So looking at this, that's got 5 carbons, that's got 4 carbons, that's got 4 carbons. More carbons, higher boiling point. This is absolutely going to have the highest boiling point of the 2. So then I look at the remaining 2. That one's got 4, and that one's got 4. Only when the number of carbons is the same are you then going to start looking at it to look for the number of branching. So both of those have 4. This one has more branching, which means it's going to have a lower boiling point. So that's 4 and that's 4. The number of carbons does not tell you which has a higher boiling point, so that's when we look at the branching. Again, if the number of carbons is the same, you look at branching. More branching means a lower boiling point. So these both have 4 carbons. This is less branching. This is going to have a higher boiling point. This is 4 carbons with branching. This is going to have the lowest boiling point. The number of carbons, the higher number of carbons, higher boiling point. Again, only when it's the same number, you then start looking at the branching to decipher that. So the hierarchy of rules, first step, number of carbons, and then only what's left over that has a matching number of carbons do you compare as far as the branch points. Does that make sense? Yeah, I feel the same way.
There's the 9 o'clock morning.
I got to work at 6:30, so I beat you.
When do you start teaching?
Huh?
What time you start teaching?
No, I don't teach during the day. No, I have a real job. I do cash now responsible. Definitely not this.
This is your side.
Yes.
What side too?
All right, almost done. You know what? I'm going to call it a night. Alright, finish reading through chapter 2. I'm going to send out chapter 3 slides. Please print them out, bring them with you next week. If you have any questions in the meantime, email me. 22 people have signed up for the homework, at least 15 people who haven't. Please get signed up as soon as possible. The course ID is on the syllabus, it's Enright Fall 18. If you have any questions or problems signing up, let me know, but the sooner we get on, the sooner we can start working on those homework, particularly for the residents. I like those problems, so I would do those problems. But, okay, if you have any questions, email me. Okay.